Atomic spectra. What is atomic spectra? When atomic gas or vapor is excited, it emits or absorbs light which varies with frequency or wavelength. This is called atomic spectra. You have two types of atomic spectra. One is your emission line spectrum, another is your absorption spectrum. How you will get emission line spectrum? When an atomic gas or vapor is excited at low pressure by passing an electric current through it, emission line spectrum are formed. Emission line spectrum consists of bright lines on a dark background. For example, emission lines in the spectrum of hydrogen. These are the emission line spectrum of hydrogen atom. Here you see the emission lines are bright lines. These are bright lines and the background is dark. Then what is emission absorption spectrum? When white light passes through a gas and the transmitted light is analyzed using a spectrometer, we found some dark lines in the spectrum. These dark lines correspond to the wavelengths found in the emission line spectrum. This is called absorption spectrum. So basically absorption spectrum are dark lines, and we generally analyze absorption spectrum by the help of spectrometer. What is spectral series? In 1885, a Swedish school teacher, John Jacob Balmer, first observed the visible region of the hydrogen spectrum. This is the visible region of hydrogen spectrum. From this spectrum, he found that there is no regularity in the spectral lines of hydrogen atom. You see, here the spectral line is broader, here less broader like this, and also the gap between the spectral lines are not regular, but the spacing between the lines in a particular series decreases in a regular way. This series of spectral lines is called Balmer series, and the spacing between the lines in a particular series like Balmer series that decreases in a regular way. You see here the spacing is more, here less. So the spacing decreases as the wavelength decreases. So this was from the experimental finding due to Balmer that there is no regularity in the spectral lines of the hydrogen atom, and there is the spacing between the lines in a particular series as we have seen in Balmer series decreases in a regular way. And if you see the series, then Balmer series, then you will find that line with the longest wavelength. This is the line with the longest wavelength. That is, the wavelength is 656.3 nanometer. This line is basically a red line, and we say it as H alpha line, and the line with the wavelength 486.1 nanometer, this line which is next to the red line, this line is a blue green line, and it is basically called H beta line, and the line next to H beta line is your H gamma line with wavelength 434.1 nanometer, and so on. So this was the observation from Balmer's experiment, and from the experiment Balmer found that as the wavelength decreases, the lines appear closer and weaker in intensity. From experiment Balmer found a empirical formula, and the empirical relation is 1 by lambda is equal to r into 1 divided by 2 square minus 1 divided by n square. And this is called Balmer formula. Here lambda is called the wavelength and r is equal to 1.097 into 10 to the power 7 meter inverse, which is called Rydberg constant. And in this empirical relation, if you put n is equal to 3, here n is equal, you can put n is equal to 3, 4, 5, the integral values. First, if you put n is equal to 3, then 1 by lambda will be equal to 1.522 into 10 to the power 6 meter inverse, or lambda will be equal to 556.3 nanometer. And this wavelength correspond to the H alpha line. Similarly, if you put n is equal to 4, you will get lambda value is equal to 486.1 nanometer, which is called the blue-green line, that is the H beta line. And if you put n is equal to infinity, then lambda value will be equal to 364.6 nanometer, which is the shortest wavelength in Balmer series. Other series of spectral lines or spectra of hydrogen were subsequently discovered. These are known after their discoveries as Lyman series, Bastian series, Brackett series, Pifford series, and these are represented by the formula 1 by lambda is equal to r into 1 by 1 square minus 1 by n square, where n is equal to 2, 3, 4, that is the integral values, and here you put 1 square. For Lyman series you put 1 square, and Lyman series is in the ultraviolet region. Remember, Lyman, you cannot see Lyman series because it is in the ultraviolet region. You can indirectly verify the series, but you cannot see it. It is not in the visible spectrum. Similarly, for Bastian series, in the empirical relation will be 1 by lambda is equal to r into 1 by 3 square minus 1 by n square, where n is equal to 2, 5, 6, 4, 5, 6, etc. And remember, Bastian series is in the infrared region. This is not in the visible region, it is in the infrared region. Similarly, Brackett series, which is the empirical, for Brackett series, the empirical relation will be 1 by lambda is equal to r into 1 by 4 square. Remember, 1 by 4 square minus 1 by n square. Here you put n value is equal to 5, 6, 7, like this. And Brackett series also is in the infrared region. Both Bastian series and Brackett series, they are in the infrared region. And for Pifford series, you use the empirical relation 1 by lambda is equal to r into 1 by 5 square minus 1 by n square. Here you put n is equal to 6, 7, 8, like this. And you can also write the Balmer formula in terms of frequency. If you write in terms of frequency, it will be equal to nu, that is equal to rc into 1 by 2 square minus 1 by n square. Because you know c equal to nu lambda, where nu is the frequency, lambda is the wavelength, c is the velocity of light. So 1 by lambda will be equal to nu by c. So if you replace 1 by lambda by nu, then this formula will be equal to, if you replace 1 by lambda by nu by c, then the formula will be equal to nu is equal to rc into 1 by 2 square minus 1 by n square. So you have to remember the Balmer formula either in terms of wavelength, that is 1 by lambda is equal to r into 1 by 2 square minus 1 by n square, or in terms of frequency, nu, that is nu is equal to rc into 1 by 2 square minus 1 by n square. So in this video we discussed about atomic spectra, and in the next video we will discuss about Bohr model of the hydrogen atom. Thank you.